Yes, can anyone have to confirm whether my screen is visible to all of you?
Yes, sir, it is visible, sir.
Yeah. Very good evening to one and all. Uh, Thank you, madam, for the warm introduction. Myself, Dr. Venkatesh. Presently, I am working as professor and head at the Department of ECE, Science Institute of Technology. It is in Bangalore. And I'm also serving as EXCA member at IEEE Bangalore section. At IEEE Bangalore section, we have IEEE Photonics Society. So wherein we want all our photonics and who the research scholars are there and doctorates are there who are in photonics or quantum technologies. I welcome every one of you to IEEE Photonics Society, wherein we will get a lot of professional networking throughout the global, not only in India. So we can get connected and we can do a lot of activities. So it may be research collaborations, or it may be joint proposals writing, and collaborating for any technical workshops like this, and FDPs, and even joint any of the collaborating activities. So with this brief introduction, so I'll start with my today's presentation. Since this topic is very general, so there is a research trends and methodologies in photonics and quantum technologies. In my talk, I started like this. I started with photonics technologies. What are all the various other applications of photonics, starting from waveguides, then sensors, then communication. Then after that, a little bit I'm talking about the quantum technologies also. Yes, these are my presentation slides. So I'm starting with photonics introduction and its applications, and I'll go with quantum computing and their applications at the latest, right? As all of you know, photonics is a science and technology of generating, controlling, and detection of light. So that is how we are controlling the manipulation of the light in the waveguides, or it may be in the any photonic structures. And at the present, we have a huge demand for the quantum technologies. So we also very well aware that government of India also it is promoting quantum India mission, and they're pumping a lot of money for the young researchers and even the startups who have the ability to start any research work which is based on quantum mission. And these both the fields, either it may be quantum or photonics. So we have tremendous applications. So it may be with respect to the sensors part, or it may be the display applications, or it may be the communication. So it has huge applications in almost all the fields. And even nowadays, this particular quantum technology, so we are adapting for the secured communication, that is quantum communication using qubits, and it gives lot of security for the radar and microwave photonics applications. Now, to distinguish between the photonics and quantum technologies, so in photonics, the main controllers are photons. Whereas in the quantum technologies, we deal with something called as qubits. And in the main goal of the photonics is high-speed communication and the controlling of the photons at the C-band or at the visible wavelength based on the application. And in quantum technologies, we have to explore exploiting quantum advantages beyond classical limits. And in the photonics, we have multiple technologies. It may be sensors, or it may be display applications. Multiple applications are there. Now there is a huge demand for the quantum technologies. It is rapidly growing, and even the research and development also. It is a tremendous future is there in the quantum technologies. The major challenges in the photonics are, as we know, it is nano devices. So we need precise fabrication and testing in the case of photonics. And in the quantum technologies, the major problems we faced come across is one is the decoherence and the error detection. And with respect to strengths, the photonics is it is ultra fast, high bandwidth, and it is low power consumption. And whereas in quantum technologies, it is excellent security, that is unbreakable security and exponential computing power. And to start with our photonics, so the majorly almost all the photonics applications if we consider, so the principles involved are one is the wave particle duality, and you must well versed with all the Maxwell equations if you want to solve any research on any of the waveguide theory or refractive index based sensors or SPR sensors. The researcher or whoever is starting the research in photonics, you must be well aware of wave equations theory and all the Maxwell equations. And the next one is the optical dispersion, where the variation of the refractive index with wavelength, it is essential for all the optical, that is refractive index based structures. And one more is the polarization, so which is the control of light's electric field, orientation for sensing, communication, and then imaging. And here, the interference and diffraction, wherever the applications are involved, so which enables holographic grating and interferometers. And 1 minute. Can you see my screen? Madam, can anyone of you confirm?
Yes, sir, it's visible.
It is visible. 1 minute. Yeah, thank you. So these are the core mechanisms. One is interference and diffraction, absorption and emission. See, in the interference and diffraction, so we come across multiple applications. It is starting from gratings, photonic crystals, all the waveguides, and all the SPR, all the sensors which are based on refractive index sensing. And whenever we design any of the optoelectronic devices, so we mainly come across these two principles. One is the photonics absorption, or other one is the emission of photons. So these two particular principles we basically deploy in the applications wherein whenever we want to go for designing any of the organic light emitting diodes or organic solar cells. So we need these particular principles. And the nonlinear optics, so it is very, very important when it comes to the frequency doubling and parametric oscillation and super quantum generation. And the optical resonance, so wherein wherever we find the applications related to the resonance, like if we have come across ring resonators or any resonating applications, so that can be used for sensing applications, or even the photonic crystals, if we design as a ring resonator by using the line defect or point defect. So we need the principles of optical resonance. And in all the principle in the above applications, we have to make sure that this is waveguiding is very, very important, and the confinement in the active layers, whether it may be the core region or it may be the active layer in either LEDs or whether it is solar cells. So we have to well aware of these particular core mechanisms, that is guiding principle and the confinement principles. And these have tremendous applications in photonic integrated circuits and all the fiber optic systems. And basically, if we classify the applications of all the photonics applications, so it has majorly, there are multiple disciplines are there. So the major ones I have listed here. This is from the latest reference from the IEEE Sensors Journal. Uh, we'll start with the photonic crystals. So wherein it is just like your TIR and um, line defect and point defect based. So we can go for designing point defect based devices, or it may be on the line defect based devices. So this photonic crystal has wide applications in both communication as well as sensing, and even on the optical devices. Next is plasmonics, so wherein we deal with both refractive index materials as well as on metallic layers. So here we come across the principle called as surface plasmon resonance. So even this SPR waveguides are by using this SPR principles. So we can go for either imaging applications, or there are some applications related to sensors also. And the next category is pure optical waveguide. So here multiple waveguides are there, starting from planar waveguide to hollow core waveguides. Okay, so there are multiple waveguides are available. So for all the waveguide applications, that is for the high speed optical signal transmission, so we can go for designing optical waveguides. And as we know, optical fiber is the old technology. Okay, so here just core and cladding principle. So and this is just based on total internal reflections. So these optical fibers we can use it in multiple applications. It is not only for the communication purpose. Apart from the communications, we can go for sensing applications also. And even there are multiple sensors available based on the uh, optical fiber phenomena and the core uh, guiding phenomena. And this is the latest technology, that is meta surfaces. So these meta surfaces, so which are more commonly used in nowadays, both in photonic structures as well as RF devices. So if any research scholars are there who are working on RF devices or antennas, these meta surfaces we commonly use to modify some of the features and some of the parameters, both in RF as well as photonic structures. And nowadays, we know, so it is silicon, semiconductor, India mission, all those things. So everything like when you consider the VLSI chips or photonic integrated circuits, the basic material will be silicon. So now, so everything we can integrate on a chip. So in the photonic circuits also, so whatever the components we are talking about, every optical structure, so that can be integrated on a common chip that is on the silicon platform. So it may be by using silicon wafers. Okay. So that everything can be, it is embedded on a very small chip, that is photonic integrated circuits. So this is the present latest uh, technology that we can combine both optics as well as semiconductor principles. So in this way, we can achieve high-speed communication. So it may be with respect to communication purpose, or it may be with respect to sensors perspective. And these are the various diverse domains in the applications concerning the photonics. One is chemical sensing. One more is telemedicine, organic chemical sensing, calorimetric sensor, and we use multiple sensors in medical diagnosis as well, and bioimaging applications, and environmental monitoring, disease detection, and glucose monitoring. So in almost every applications, we can see these devices are either lab on a chip devices, or it is very miniaturized devices compared to the traditional whatever the glucose sensors available. These photonic sensors are very small in size and very accurate and high-speed devices. Now, if any research scholars are available here, the common platforms available to pursue your research are these are the very most commonly available softwares. One is console multiphysics, so wherein we can use both ray optics, wave optics, and you can combine any physics that is required for your simulation purpose. Next, we have ANSYS optics tool. Okay, that is also very popular, and we have uh, multiple softwares are available within the ANSYS. So it may be semiconductor module, heat transfer module, charge carrier module. All uh, all the solvers are integrated within these softwares. One more we have Opti BPM, that is the Opti beam propagation method. And the scholars who are working on a system level, like it is just similar to the PSpice or multisim, where we can just drag and drop the elements available, and we can enter the parameters related to each of the optical component. Okay, that is Opti system. Those who are interested to start the research, or those who wanted to use this Opti system, so we have created a separate working group for them. Later, once my talk is over, I'll share that WhatsApp group link. So from this month onwards, we are going to start a series of talks, so which enables all the research scholars, the doctorate holders, on how to use the TAPRI system. And even they will also, the company has agreed to provide 3 to 6 months license, so you can work on and you can use that for your research as well. Uh, Next, with respect to the quantum communication, as we know, the present trend is towards quantum. Related to quantum, so there are multiple platforms are available. So the most popularly used softwares are the tools are one is Qiskit, Circ, Qt, and Pennyline. And this Qiskit is, I think, it is sponsored by IBM. So it is one new login account we can create, and we can start working on simple gates or quantum circuits. We can build our own circuit, and we can see how exactly it is working with respect to the functionalities concept. Now, to start with the quantum computing, so it is started earlier. So from the classical computing to the quantum computing, is the main person that is David Dutch developed the quantum Turing machine, showing the quantum circuits are universal. And in the 1994, Peter Shor he came up with a quantum algorithm to factor very large numbers in polynomial time. And he has demonstrated a very complex problem can be simulated or it can be solved within a fraction of seconds by using supercomputers. And in the 1997, Lou Grover develops a quantum search algorithm. Okay, this is also for solving the complex problem and which involves a lot of computational time. So he has also demonstrated that so any complex simulations or any complex which involves high computing time that can be solved very quickly by using the principles of the quantum computing. That is just see these all these are so like compared to our traditional computers. So these quantum computing, so which deals with qubits, that is ket 0 and ket 1, and the one specialty of these qubits is like we cannot say whether it is there in zero state or one state at any point of time. So it can be neither one state or zero state. That is a superposition. That is the major advantage. And in 1982, the Feynman proposed the idea of creating machines based on the laws of quantum mechanics instead of the laws of classical physics. So, because of the inventions from these famous scientists, now today we are seeing the actual strength of quantum mechanics as well as quantum computing. And now the technology is already adopted in the military and radar applications, wherein we are already deploying this quantum communication using with the help of the latest technologies such as quantum machine learning for high secured communication. Okay, and whenever we are dealing with secured communication, the security is very, very important. Okay. So in quantum computing, by using the traditional quantum key algorithms or quantum security algorithms, it is a very challenging task for any intruder to discover the encryption and decryption key. So the studies tells so it takes few years to decode any of the key that is used in the secured communication by using quantum communication principles. So these are just some basics that is quantum computing. So which is emerging field and it deals with quantum mechanics and the basic principles are superposition, entanglement, and quantum interference. And it is beyond classical limits. And these are some of the research centers we have already adopted the quantum computers. One is IBM Quantum Research Labs, Google Quantum AI Lab, MIT Lincoln Laboratory, Harvard Quantum Initiative, Delft University of Technology, and many more. And almost all the research centers in India, IAC, all the institutes of national importance. So now they are setting up the labs which are related to quantum computing and quantum technology. Now to just start with the quantum technologies, okay, so compared to our classical computing, our quantum computing deals with qubits, that is ket 0 and ket 1. And these principles are very, very important. That is, one is a superposition theorem, and one more is the entanglement. Okay, these are very critical phenomena in quantum computing. And already we know we have reached the lower limit for the chip size in the VLSI. like according to Moore's law. So already we have reached the whatever the least dimension that is possible. And already now we know, so the presently IBM is working on 3 nanometer technology. So if you want to go below that, then we need a different technology that is quantum. So the next technology, what we can expect is the circuits also that will be fully that is functional based on the quantum principles and quantum circuits. So these quantum circuits are entirely different than our regular VLSI circuits. And to just to imagine the representation of qubits, now here I have taken a simple example. Now I have taken two electrons, one at the ground state level and one at the excitation level. The ground state electron, so it is assumed as ket zero. So this symbol is ket zero, and the excited state is just we are imagining as it is ket one. Okay. Now these states, like this is single qubit. Single qubit means the only two possibilities are there. One is ket zero state or ket one state. So this is ket notation. And if you go for 2 bits, you will get four combinations. If you go for 3 bits, it is just like a simple logic design column, like 2 to the power of n. It is same thing. So suppose if I consider a 3-bit qubit register, so it will have 8 states, 2 power 3. Okay. And the first coefficient, so this is the wave function that is psi. And this particular coefficient for all the different combinations. So like if you take any 3-bit logic gates, so we will be having 2 to the power of 3 state. That is total 8 states starting from 000 to 111. So in the case of 3-bit quantum register, so we indicate all those states as uh, ket 000, ket 001 up to ket 11. So the initial coefficient, whatever you are observing here, this gives the probability. This gives the probability coefficient is amplitude coefficient. Okay. So suppose if I for this particular wave function, whatever we have written here, these coefficients, all these coefficients, whatever you are seeing, that is 1 by root 8. So how it comes is it is 1, the probability will be 1 over root of 2 to the power of n. So here the number of bits are 3. So this coefficient we are observing as 1 over root 8. Now suppose if I take the magnitude of this, like the total probability, that is the amplitude of the first state, that is 1 by root 8 square, plus the second state 1 by root 8 square. So if I sum up all these coefficients squares, so that I should get the total probability. It must be always equal to 1. Now here I have taken one special example wherein we have in the first case it is ket 0. So in the second case, you can see the electron state. So it is neither at the ground state nor at excitation state. So it is in between both the states. So this state can be written as superposition state. So I can call this state as ket 0. And neither I can say it is ket 0 nor it can be said it is ket 1. So this is superposition. It is both the states are available here. And this is the same. Suppose if I want to express this wave function, okay, that is a wave function in terms of matrix notation. This is how we represent. So it is like ket psi. So I will indicate it as these are the alpha and beta are the matrix coefficients of the states. One is ket 0 and ket 1. There are two coefficients are there. One is alpha and one more is beta. So the condition here it is the total probability, that is the alpha square plus beta square. So it must always give it is 1. And these are some of the mathematical operators that I have mentioned here. So which are different from the regular linear algebra. So one is inner product, one more is the outer product. You can see the notations here. There is a small changes here. Okay, and that we have to observe. And one more is a tensor product. So this tensor product, it is not similar to a regular matrix multiplication. So which gives higher order multiplication, and there is no compulsion that the number of columns in the first matrix must be equal to number of rows in the second matrix. Irrespective of that, we can do this particular tensor product operation. And this property is very, very important. This is the reversal property. That means these quantum gates are reversible. That means we can predict the input states based on the output state. And the one major property that all quantum gates needs to be satisfied are, that is unitary property. Okay, so this unitary property, that is U degar into U. So this must be equal to the identity matrix. And these are the few more requirements for any of the wave functions. The total probability, as we know, the probability is always greater than or equal to zero. And if you take the overall PDF area, that is the integral over psi, that is a wave function. So this must be always equal to 1. And these are some of the standard quantum gates, so which are familiar to all of us. So those who have started their research, or those who are learning quantum gates, they'll start with single operators, starting from Foley X gate, Foley Y gate, Foley Z gate, then Hadamard gate, phase gate, and 5 by 8 control NOT gate, and control Z gate, okay, and Topoli C NOT gate, okay. And the one thing we have to observe is all these gates are reversible. Okay, that means from the output state we can predict what is the input. But this particular condition, it is not true for traditional logical gates. For example, if I take a simple AND gate, is it possible to determine what is the input states by knowing the output? Any one of you? Is it possible? Am I audible? Am I audible?
Yes, sir. It is audible, sir. Yes, sir.
Yeah, thank you, Audible. So just I'm taking one example. Suppose if I take one 2-bit AND gate, so which has two states A and B, okay? So it is 0, 0 is one state, and 0, 1 is one state, and 1, 0 is another state, and 1, 1 is the last state. And for the last combination, we can say straight away it is the output is 1, okay? And remaining all the states, for the first state it is 0, okay? And second state it is 0, and the third state also it is 0. Suppose if I ask you one question, if the output of the AND gate is 1, what is the input combinations? It is the known answer for all of us. So it is 1, 1 is the input combination. At the same time, if I ask one more question for the output 0, if I ask you what is the input combinations, then it is a probability is 1 by 3. You can see there are three possibilities are there for the two input AND gate. That is three combinations. It is giving the same output, that is 0. Whereas for these quantum gates, if I say what is the output, if I ask you, if I give the output, you can directly say what is the exact input combination. That option is there for all these quantum gates, whatever we have listed here. In the traditional logical gates, or the whatever the gates are available, that option that is not true. So even if I go for higher order states like a 3-bit AND gate or 3-bit OR gate, you can check for various cases. So if I go for 3-bit AND gate, it will be total combinations are 8. Only for one combination, I can predict the actual inputs. That is the last case, where in triple one, it gives output 1. Remaining 7 cases, the output is 0. Then for the output 0, the input combination possibilities are 6. Okay. So whereas for these quantum gates, you can see one good observation is they must be reversible. So this is the very good um, property of these quantum gates. Now, the advantage of this particular property is, so um, we can predict the input combinations by knowing the output. So even for input combination also we'll be knowing the output, and from the output also we can directly predict what might be the input combination as well. Whether my slides are changing? No.
So now quantum gate slide is visible, sir, right now.
Yeah, I think I cannot. Yeah, I think now I can change. 1 minute. Yeah, thank you. I think now you can see the next slide. Am I right? Is it visible?
Yes, sir. Key challenges in quantum.
Yeah, yes. Key challenges. So the key challenges in quantum computer, one is decoherence and noise, error correction, and the scalability. So these are the key challenges in quantum computing. Then the hardware challenges is one is the process, one is the high cost and complexity. Even if any research institute, if they want to establish this particular lab, they have to invest a lot to establish this particular lab. That is the initial cost involved in the setting up the laboratory or setting up the facilities. It is huge. And one more is it requires cryogenic cooling, that is less than minus 150 degrees centigrade. So we have to maintain at minus 273 degrees centigrade. And the limited software tools, like as I mentioned earlier, so we have very limited and many are emerging, and many of the startups are also coming up. And the major tools are here, Skids, here, Companion, and D-Wave. And it is the very smart, one interesting YouTube link I have provided. I think you can see. Is it visible?
Yes, sir.
Yeah, yeah. Thank you. It's that one, right? I think that video is having some problem. I think, can you see my slides now?
Yes, sir.
Yeah. So I'll try playing this
Slides
video.
okay, sir, but video is not.
Yeah, now, madam?
It's okay, sir.
Yes. Yeah.
Sir, video okay, but audio is not audible, sir.
Audio. Okay, okay.
No audio.
Now, madam?
No, sir, there is no audio, sir.
Okay, okay. I think let me stop it. Yes. So that was a very small video. So now let us just discuss about some of the future prospects or future applications where all are working for. So am I audible, madam?
Yes, sir.
Yeah. So these are some of the latest trending real-world applications of quantum computing. One it is in the cyber security, AI and machine learning, drug discovery and material science, and finance and logistics. So in the cyber security, so the major principles are one is quantum machine learning and quantum encryption and quantum decryption methods. So in case of AI and machine learning, so as we know, AI is a trending word now, and machine learning, and that is already adopted in quantum as a quantum machine learning. So that is mainly used in either communication purpose, or it is mainly used in some of the sensing applications as well. And in the drug delivery and material science, so there is a lot of scope for invention of materials which are compatible for the quantum technology or quantum based devices. Okay. And these are some of the, suppose any one of the research scholars who wanted to start their career or to start their research. So in this quantum computing, so these are some of the prerequisites, so which are mainly essentials for learning this quantum tools. One is the basic Python. Suppose if you wanted to start with IBM or Qiskit, so or just from Google Colab also you can start simulating any of the quantum circuits. So we need basics of either Python programming, and we must be strong at linear algebra and probability theory, and we must know any one of the quantum based simulators. So it may be Qiskit, or there are multiple softwares are available. So we have to learn any one of the tools. And the next one is the top computing companies. So we can just we can see what is IBM, Google, D-Wave, Amazon. So what exactly they are doing and what are all the various present facilities which are available. So once we visit, so this is also new for all of us. Okay, so once we visit these companies or visit the quantum labs, so we exactly know what exactly the technology and where we can contribute in the research and the present quantum India mission. And for students, there are multiple opportunities are there to start their internship or PhD scholars for their research foundations. And these are some of the learning platforms which are already created in Microsoft Quantum, MIT, and Harvard Labs. There are online learning platforms also available, wherein we can log in and we can see the resources available in this particular website. So these are the main resources for further learning. One is IBM Quantum Learning, that is a skip tool, and Quantum Computing Fundamentals by MIT Expro. And third one is quantum computing courses on EDX, and a practical introduction to quantum computing by CERN, and the complete quantum computing course in Udemy. So these are some of the learning platforms which are available to start any of the research scholars or students on this particular new technology. And with respect to the applications are concerned, as I told, the quantum materials, it plays a huge role. Now we can see almost all the display applications as well as the sensors. We are using quantum dots as a additional layer. So either to improve the performance parameters of either absorption-based devices or emission-based devices, or it may be in terms of sensors. So in the quantum dots, the size plays a very huge role, and there is a lot of scope for the materials that has to be used, and even the material scientists also they can contribute a lot in the field of quantum computing. So with respect to quantum dots applications are concerned, so it has tremendous applications in photolimitations applications. There is a high display as well as sensor applications and computing devices. As I mentioned earlier, so these quantum dots, they're mainly used in the display technology. So you might have heard that there are multiple Display types are available, starting from wearable watches and even devices. So almost all the applicable displays, that is very QLEDs.
Excuse me, sir. Voice is not audible, sir.
Am I audible, madam?
Now it's okay,
Yeah,
sir.
yeah, yeah. Yeah. So just I was telling about the quantum dot applications. So the quantum dots are mainly used either it may be for the photoluminescence applications or biocompatibility devices. So with respect to the display applications are concerned, nowadays we are all wearing the display. It is either based on either QLED quantum dot based light emitting devices displays, or it may be in the TVs, or it may be on the wearable watches, or it may be on the any devices, whatever the optical nano sensors are there, it may be on the photonic crystal based or SPR based. So wherein just we can use a layer of quantum dots, so we can see how exactly the performance parameters are improving. So it may be the sensitivity or the detection limit. So we have to play with multiple parameters like material properties, the placing this quantum dot layer on the active layer or on the conductive material or on the guiding layer. So it will tremendously change the behavior of the optical sensors. So it has mainly we are using both in the display applications as well as biomedical applications. So now in the future we can expect the quantum displays which are very thin and the high resolution. So both are very, very important in the case of display applications. Whereas in biomedical applications, already the sensors are miniaturized. So by using this dots based sensors, still we can get a lab on a chip ultra miniaturized sensors. And also this particular quantum dots, so we are using in photonic circuits, or it may be in the lasers technology, that is quantum based optical devices. Like if you want to go for quantum communication, so we need single bit photon sources. Okay. So there is a lot of scope for researcher to start with any of the research which are focused on generation of single bit photons. It is very, very challenging. Okay, so it is much different than the traditional LED design like active layers. Either it may be the layered structure. Okay, so the confinement of single photon is very, very challenging. So wherein we have to focus a lot on the materials which are compatible for this particular application, and single emission of photons at that particular given wavelength. It is a very challenging one. And even these quantum dots are used in optical sensors as well, and quantum communication and integrated photonics. So this comes in under optoelectronics as well as photonic integrated circuits. And it is once again it is repeated. So it is the quantum dots are mainly used in display applications. Even it is in the um, organic solar cells or organic solar cells. So we need this quantum dot layer to improve the performance parameters of solar cells. So it may be the conversion efficiency, or it may be the electron absorption rate. So that absorption rate can mainly controlled by properly placing quantum dot and suitably designing the quantum dot layer, and that incorporation of quantum dot layer in the solar cells structure. And also some of the imaging applications is concerned. So whenever so if we go for any lithographic applications, so when you wanted to design any of the imaging devices, so these quantum dots layers addition, so it will significantly improve the resolution of optical imaging, and it gives much higher resolution, and we can see much inner details of any of the nanoparticle or nano dimension based devices. And these are some of the challenges that are based in quantum dot space solar cells. And in the case of lasers is concerned, so it has main applications in telecommunications for communication purpose. And we use quantum dot based lasers in medical imaging, and it is also used in display technology as well as sensor development. The role of quantum computing information. So Here, the quantum dots, as well as the application of quantum dots in laser applications. And these are some of the mechanisms involved in quantum computing and information. So these are some of the future directions in quantum dot research. Now, this is just a prediction. So now we are in this particular state, that is the invention of new materials and commercial usage, introduction of quantum dots in consumer electronics. So in future, we can see it is just a prediction. This I have copied from the internet sources. Okay. So in by 2027, so we can see that is a improved emission, enhancement of emission properties for displays, and there is a lot of already some materials are available. Still, there is a lot of scope for new materials that are compatible for quantum computing or quantum-based devices. Okay. Next, by 2028, that is biocompatibility research on biocompatible quantum dot materials. And 2029, there is a significant improvement in solar cells, that is the integration of quantum dots in photovoltaic technologies. By 2030, so it is we are predicting nano sensing, use of quantum dots in environmental monitoring. And 2031, that is policy frameworks, establishment of regulations for quantum dots and applications. That means in another 5 to 7 years, we can see there is a huge leap for the quantum researchers, and we are expecting multiple new devices and new technologies, so which are much accurate than the present existing ones, are much higher resolution than the present devices are concerned, which are based on uh, optics, that is nanotechnology and optical applications. So this is the one more slide, which is based on integration with other nanomaterials. So we are here, that is quantum dots, so that are highly compatible with semiconductor as well as nanocrystals. Okay, because this we can combine with our present semiconductor device, that is VLSI chips. And the second one is the metal nanoparticles, that is small metallic particles. And we can also integrate with the one of the most promising materials, which has given tremendous applications in both sensors as well as all the nano based devices, that is the graphene, so which is single layer carbon sheets. And the fourth one is the enhanced photonics, and the fifth one is sensing applications. Sixth one is conductive composites, and seventh one is the multifunctional materials. So there is a these all these components or all these particular technologies we can integrate on a common platform, and your quantum dots are much compatible with all these particular technologies. And this is the one of the very useful and much secured communication, that is quantum communication, that we are adopting in the radar technology, wherein we need secured communication as well as very high resolution images to be taken from the space. So it is enhanced detection, advanced imaging, and still technology capable of detecting objects with minimal radar emissions. And it is secured communication implies quantum encryption for safe data transmission. So it is the study states that, so if you are using quantum communication for transferring the data, for any intruder, if they want to detect or if they want to identify what data we are transmitting. So even if they use supercomputers, it takes a few years to decode that particular encryption key. So this quantum communication, it is considered to be the highly secured and safe transmission, and it is highly impossible task for any intruder to detect what data we are transferring. So it maintains data confidentiality as well as high secure and ultra fast transmission. And these are some of the basics of radar technology. That is one, and the applications. One is air traffic monitoring, weather forecasting, and military surveillance. And the current applications in defense and security, which these are some of the problems which are faced and what are the solutions offered by quantum-based systems. One of the problems faced is traditional radar systems struggle with stealth technology. The solutions offered is quantum radar enhances the detection of stealthy objects, and the benefits are the improved surveillance capabilities and threat identification. These are some of the strengths, weakness, and opportunities and threats of quantum radar. And these are some of the learning resources. So the research scholars or faculty who are interested in. So you can just refer these books for beginners, and these are the most popularly used materials for learning. And these online courses are much helpful to start any basic research or start understanding any of the basic circuits and quantum circuits. And these are the companies which are already working on quantum computing and quantum research. So these are the global trends which are driving innovation. At present, there is a demand for ultra-fast, energy-efficient data transmission in both photonic integrated circuits and silicon photonics. There is a growth of cyber physical systems and security, so which uses both quantum communication and quantum key description. And we are using these both the technologies in 5G or 6G or IoT, AI, and cloud computing, both photonic data as well as optical interconnects. And in healthcare, biomedical, all the applications, we are using both optical biosensing devices as well as quantum enhanced imaging devices. And the major advantages in the by considering that quantum radar applications, it is the national security and the space one. Quantum secure satellite communication and microwave photonics. So microwave photonics is another field of study. Okay, so which is high speed and very reliable communication. And throughout the world, we can see there is a huge investment. It is from the government of India as well as other countries. So to develop new technologies on quantum based devices. So GY also it is supporting initiated Quantum India mission, and they are also inviting huge applications from all the startups, research scholars, and research centers for pursuing their research and to develop the new technologies based on the present quantum technologies. In summary, I'll conclude that so the both photonics as well as quantum computing both are exponentially speeding up with respect to the technology is concerned and applications is concerned. And there is a huge carrier potential for photonic sensors, SPR and optical imaging, and even in display and sensing applications, and even in nanotechnology, so which uses both material science as well as metamaterial based optical imaging sensors. And quantum cryptography is another field, so wherein we can do a lot of research on quantum key distribution and quantum secured algorithms as well as. And quantum AI and machine learning is one of the emerging field. So it also has a lot of applications in quantum communication and space and radar applications. It is the need of today for every all the countries. So wherein we have to protect and we have to safeguard any of the data that is sent and whatever the threat that is from the other countries. So we need to strengthen our country's military strength that is mainly based on by using quantum-based radar devices. And the one more major advantage is the security. The security is from by using this quantum communication very high, and it is very challenging to decode any of the data. And sensing applications, it may be imaging applications, or it may be the normal biosensing applications. So with this, I thank the organizing team and AICTE and all the faculties uh, for your patience in listening. And this is my LinkedIn QR code. So those who are interested can please connect to me. And I am representing IEEE Bangalore section Photonic Society. I will be the chair for next year. If any research scholars are there, those who are willing to enhance their skill set, or those who want to learn any of the tools. So we do conduct a lot of awareness and training sessions as well as multiple workshops, faculty development programs. So which is almost free for all everyone. Okay, this is just to because it is a new technology. Even we are also trying multiple companies to collaborate and to give hands-on sessions for the research scholars, faculty members, and the doctorate holders. because the technology is emerging, and we need to improve our skill set as well as we keep learning to adapt with the changing world and the rapid change, advancement in the technologies. And if there are any young professionals are there, there is one small announcement from the IEEE Photonic Society. 1 minute. So if there are any queries, I think, madam, if there is any questions, I think we can take up some questions. Can you see my screen?
Yes, sir. It is visible, sir.
This is from the IEEE Photonic Society. There is an announcement. This is for the young professionals who are less than 45 years, or from the date of first graduation within 15 years from the first graduation, that is up to 40, 45 years. Those are eligible to take this particular role. That is the volunteering firm. So here, what they do is they will give some of the funding support, or it may be fellowship, or it may be with a volunteering role in the IEEE Photonic Society. That is at the global level. You will also get some additional support. It may be some of the funding support. So wherein you can involve yourself in the research related activities. They will also give some seed money for pursuing your research or to create some of the resources at your own institutions. It is just a simple form. For this, you needs to be the member of IEEE, and you have to take IEEE Photonics membership. So you can join this particular community and you can avail the benefits which are already available in IEEE Photonic Society. Now, just for all the faculty members, just I'll show some of the unique initiatives from the IEEE Photonic Society. Now, do you have another 5 minutes time?
Yes, sir.
Yes. So now this is the main website of IEEE Photonics. So wherein you can see all the initiatives, everything. And here you can see these are the major conferences. These are called as Tier 1 conferences. These are initiated from the IEEE Photonics itself. That is the major body at the global level. So these are some of the flagship conferences. One is IEEE Photonic Conference, that is IPC, which happens every year. IEEE Summer Tropical Meeting Series, some IEEE Silicon Photonics Conference, IEEE Rapid, then ETOP, OFC, CLIO, and CLIO EU. So there are almost some 8 flagship conferences are there, which are initiated from the IEEE Photonics Society. One key advantage is suppose if there are any research scholars are there or young professionals are there who are recently graduated. So for them, for all these conferences, they will provide travel grants. So it is up to 2,500 US dollars they will give. In a year minimum, they will give some 10 to 15 candidates they will give. For that, the minimum criteria is the author must be first author. So complete 2 and 4 flight charges, accommodation, registration, everything will be covered in that particular travel grant. So they can aim to submit the research for these flagship conferences, which are initiated from the IEEE Photonic Society. And one more is there, that is some of the resources. So one is sponsorship, and to attend some of the meetings also they will invite. And there are some education related tools are available. One is the Career Center, then IEEE Photonics Journal Club, okay, and then student resources. If you go for student resources, there are multiple student resources are available for students to learn and to improve. Okay, so these are free for almost all the members, and it is a if even though if you're not IEEE member, you can just see what are all the facilities which are available for students. Some of the resources. One is IEEE Student Professional Awareness Activities. So if you click here, you will come to know almost all the activities which are initiated by IEEE Photonic Society. And this is one of the recognition IEEE HKN. And some of the IEEE offers multiple benefits for student members. One is IEEE Extreme Programming Competition, so which happens every year. If your college has IEEE student branch, Photonic Society, So you can apply for student branch awards, student professional awareness, and then program. So this is one of the very good initiative from the IEEE Photonic Society. The students who are in need of any scholarship amount, that is after graduation. So here they can apply. For that, there must be a research. They have to start their research in any of the domains. Okay, so with the recommendation of any faculty advisor, so they can apply for this particular IEEE Photonics Graduate Student Scholarship Program. So it is up to 5,000 to $10,000. They will support, and even there is a career page is available for all the members. And these are some of the publications if you check. So if you become the IEEE Photonics member, all these journals are free to access. So if you have photonics in your IEEE card, so you can access all the papers from IEEE Photonics Journal, IEEE Photonics Technology Letters, IEEE Journal of Quantum Electronics, IEEE Optica, Journal of Lightwave Technologies. All those are free. And these are some of the clubs. These are global clubs. You can join to these clubs and you can be part of global resources or resource persons available in photonics technology. And this is one more thing, that is the IEEE Photonics Society Fund. Because I think almost all the participants who have joined, they are faculty members. So getting funds from government agencies, it is a bit challenge and it is a very high competition. So many faculties they don't know from the IEEE Photonics Society. If you have any of the small ideas or any research proposals or any event if you want to plan, you can submit just like this FDP. They can plan one FDP on a specific theme and they can submit here. And these are some of the major areas. Yes. IEEE Photonics Society gives funding for one is a society for any of the activities. But before that, we have to approach the treasurer to get this grant. And annual travel grants, as I told, for almost 7 to 8 conference, they'll give annual travel grants and educational seed funding and IEEE site funding, then public imperative initiatives and global consortia partnerships, actively humanitarian activities in the developing nations, support for global members and remote communities. So you can almost approach and you can write to the president of IEEE Photonic Society for any funding is concerned. And there is one more separate page is available, careers. And this is the global community. So this particular community has almost one more than 160 chapters and affinity groups, and more than 370 photonics research centers. And as I mentioned, IEEE Photonics Society organizes major more than 8 flagship conferences, and there are 9 publication and technical journals are available, and more than 100,000 plus mentors are available for volunteering. And 12 prestigious awards will be given by IEEE Photonics Society every year across the world. And these are some of the social media websites for IEEE Photonics Society. You can connect it with IEEE Photonics Society for any of the queries and any of the funding opportunities. Yes. So with this, I conclude my talk and I stop presenting my screen now. Any queries from the audience?
Participants, if you have any queries, please raise. The forum is open for you. If you have any queries, you can post in the chat box also.
Madam, I'll give one WhatsApp link wherein we are starting one photonics lecture series on optics tool. Uh, that particular series, which mainly focus on only the hands-on sessions. All faculty they can learn that particular tool for free, and even the company has agreed to give some 6 months license. The faculty or students they can start their research on uh, uh, quantum devices. So just it is a drag and drop, but we need to know the understanding of how exactly the sources, the passive devices, even the analyzers, so that we have to use, and we can develop multiple applications using that particular tool. I'll share it to the organizer. So if any are interested, you can join that group. And we are planning to host that series of activities from the next month onwards.
But I think no more queries.
Yeah. So online
Yes,
means
sir.
I think there is no queries from the audience side.
Yes, sir. Yes, sir.
Yeah.
So, thank you so much, sir, Dr.
Thank you.
Venkatesha, sir, for investing your valuable personal time and for patiently taking us through such a vast and rapidly evolving domain. And now I would like to give the summary of the insights given by Sir on research trends and methodologies in photonics and quantum technologies. The way he connected the fundamental photonics wave, particle duality, interference, diffraction, nonlinear optics, optical resonance, and wave guiding with advanced concepts of quantum technologies, including qubits, superposition, entanglement, and quantum gates, provided us with a clear and comprehensive understanding of these frontier areas. Sir has also highlighted how the integration of nanomaterials with the photonic and quantum devices is accelerating breakthroughs in sensing, communication, and advanced device fabrication. Sir has given brief insights on tools like COMSOL, ANSYS Optics, OptiBPM, OptiSystem, CERT, and Penny along with real world applications spanning telecom, 6G, defense space, biomedical sensing, quantum communication, and high performance computing. Sir also emphasized on global initiatives, the work of leading quantum labs, and the challenges of decoherence, scalability, fabrication, and error correction. Sir also provided valuable insights about the IEEE Photonic Society and the opportunities it offers for the researchers and the students to grow, collaborate, and contribute to the global photonics community. On behalf of the organizing committee as well as the participants, once again, thank you so much, sir, for your valuable time, effort, and exceptional clarity. Thank you so much, sir. We are looking forward for the same kind of intellectual interactions in the future.
Thank you. Thank you, madam. Thank you for the opportunity.
Thank you. Thank you so much, sir.
Yeah.
Participants, the next session will start in 5 minutes. Kindly stay in the same link. The next session is by Dr. Ashraf Ali Sheikh. He is an accomplished professional with expertise in teaching, guidance, and counseling. He has a strong track record in improving research activities and teaching effectively with a PhD in ECE from KL University. Sir has published several papers in national and international journals like Web of Science, Scopus, and UGC Care journals. With over 16 years of teaching experience, Sir has received many awards. He is the recipient of Teacher Award by NRI Institute of Technology for the academic year 21-22. His field of expertise involves VLSI design, machine learning, and deep learning. Dr. Ashraf Ali sir is currently working as Associate Professor in NRI Institute of Technology, Vijayawada. He is the Director, BIS Technologies Private Limited. Sir, Ashraf Ali sir.
Yes, ma'am.
Sir, over to you, sir. Please
BR
continue.
Concepts Private Limited. Thank you, ma'am. Good evening, my dear faculty members. Good evening to Dr. Vishnupriya Madam, Associate Professor, HOD Department of ECE, coordinator of this event. And then Dr. Hemlata Ma'am, Associate Professor, Vijay Institute of Technology, co-coordinator. Thank you, ma'am, giving this wonderful opportunity to me. So, right. Ma'am, is it visible? My screen?
Yes, it is visible, sir.
Sir, thank you, ma'am. So, myself, Dr. Ashraf, a director of BR Concepts Private Limited, which is a corporate training firm, and it is established in 2016. So, since then, it is a completely training and placement institution. So, then after coming to myself, I'm a certified DFT engineer, that is Design for Testability Engineer, certified Physical Design Engineer, and a certified Analog Layout Design Engineer from Chip Edge, Bangalore, and a certified Machine Learning Engineer, and also doing quantum computing. Yeah. So this is all about me. So coming to BR Concepts, it is approved by AP Higher Education Board. ISO certification also there, Startup India and Skill India certifications also there. So coming to today's agenda, so all the faculty members are discussed about more concepts. So I will concentrate on classical computer versus quantum computing and quantum computing with cloud and backend. So what are the reversible gates in quantum computing? And what are the unitary operators? Gates with single qubit, 2 qubits, and 3 qubits. And then coming to quantum circuit, series quantum circuit, how it works. Manually we can try, and then we can use the tools like Qiskit and AlgoSet tools, and then parallel quantum circuits. Then finally the entanglement states. This is the most important topic, entanglement state. And then if time permits, I will do quantum error correction up to quantum error correction. Yeah. So we will start the session without further delay. So what is the difference between classical computer and quantum computer? So simple, I put it in simple manner. Actually, classical computers are laptops and desktops. What it will do, it will fetch the instructions from the RAM and data storing, etc. etc. So what is this quantum? How can we define the quantum? Quantum means the smallest indivisible unit of energy. Quantum means the smallest indivisible unit of energy is called as quantum. So example, let us consider a light. Light is made up of small particles called quanta. So that means quantum processor entirely depends on the photons. Quanta or photon. So quantum processor entirely depends on photons, right? So if it does not contain the quantum processor, then we call it as classical computer. If it contains the quantum processor, then we call it as quantum computer. In general, the classical computers follows classical physics. What is this classical physics? The Newton physics or Newtonian physics are called as classical physics. We know Newton's three laws. Newton's first law, which gives about law of inertia. Second, Newton's second law, force is equal to ma. And Newton's third law, that is equal to for every action there is an equal and opposite reaction. So all classical computers works based on the Newtonian physics, whereas quantum computers depends on quantum mechanics. What is this quantum mechanics? So superposition, the most important topic. The superposition, interference, it will come in what you call in quantum communication, it will appear many times. Interference, constructive interference and destructive interference. If it is constructive interference, then the amplitudes increases. If it is a destructive interference, then the amplitudes decreases. Next, entanglement. We will discuss it in further slides in more detail. So because it is more important. Next, classical computers accepts binary data, that is zeros or ones. We all know logic 0 or logic 1. Whereas quantum computers accepts the superposition of zeros and ones. What is this superposition? Superposition can be represented in terms of qubits, that is ket 0 and ket 1. So what is this ket 0? What is this ket 1? How can we form ket 0 and ket 1? We already discussed quantum processors depends on photons. Yes. Suppose if a light is polarized in x direction, if a light particle is polarized in x direction, then we can get as ket 0. Suppose if the same light is polarized in y direction, then we can get ket 1. So how can we represent ket 0 and ket 1? Actually, ket 0 and ket 1 are column vectors. That is, ket 0 can be represented as column vector 1 0. Ket 1 can be represented as column vector 0 1. Since we are having column vectors, there is also row vectors are also there. The row vectors can be represented as bra 0, that can be represented as angled 1, angled 0, and then a bar. That can be represented as 1 0 row vector. And bra 1, it can be represented as 0 1. So these are the differences. Ket 0, ket 1, bra 0, and bra 1. Actually, it came from bracket. So bra is called row vector and ket is called column vector. Right. So we all know how qubits are formed. If the light rays are polarized in x direction, then we get ket 0. If it is polarized in y direction, then we can get ket 1. Okay. So in order to explain the superposition, let us consider an example. So everyone knows this example. Let us consider a coin, a 1 rupee coin, and we tossed up in the air after falling on the ground. So after falling on the ground, it will be stable. That means it is collapsed. We can say that it is collapsed. When it is in stable state, we can say that it is collapsed. Then we can measure that it is in either head state or tail state, or either it is 0 or it is 1. We can measure it after collapsing. But when it is in the air, spinning in the air, we cannot measure the value. That is either head or tail, we cannot predict. After falling on the ground only, it will collapse. It will collapse to either logic 0 or logic 1, either heads or tails. So that is called classical output. Classical output. Since in classical output 0 or 1. Similarly, here also we are getting heads or tails. That is why it is also called as classical output. So classical computer produces classical output. Whereas quantum computers, suppose on a table you are spinning a coin. You are spinning a coin. You can see both the states, that is head and tail, at the same time. At the same time, and is there, not or, and is there. So if you are seeing both the states at the same time, then we can say that it is in superposition state. It is in superposition state. After some time, again it falls on the table. It falls on the table. That means it is collapsed. After that, we can measure either head or tail. Either head or tail. So that means it changes as classical output. From superposition state to, it changes to classical output. Clear? Is it clear? So superposition means we can see both the states at the same time. Classical output means we are seeing only one output, either head or tail. So that is the difference. So quantum computers are always depends on this superposition state. When it is in superposition state only, it has the ability to simplify the complex problems. So coming to next slides. In classical computers, there is no superposition theorem. So it obeys only Newton's laws. Whereas quantum computers obeys superposition theorem. So what is this superposition? The linear combination of qubits. Hello? Yeah. Superposition means the linear combination of qubits. So what is this linear combination? We can represent it like this. Ket xi can be represented as alpha ket 0 plus beta ket 1. Beta ket 1. So what are these alpha and betas? Alpha and beta are called probability amplitudes. Probability amplitudes. Right? So suppose in order to get ket 0, the probability is alpha square divided by alpha square plus beta square. In order to get ket 1, the probability value is beta square divided by alpha square plus beta square. So where alpha and beta are called probability amplitudes. Next, it uses logical gates like AND gate, OR gate, NOT gate. We are all know logical gates. Whereas quantum circuits uses the gates like Polis gates. So the most important X gate, Polis X gate, Y gate, Z gate, and Hadamard gate, which is represented with H, and phase gates, S gate and T gate. S gate and T gate. We will discuss in more details in further slides. Next, NAND, and we all know NAND and NOR are called universal gates. NAND and NOR. Sorry. Ma'am, any doubt?
So, sir, please continue, sir.
Yeah. So NAND and NOR are called universal gates. We all know what is universal gates. We can realize all the gates by using NAND and NOR. So remaining gates like AND gate, OR gate, XOR gate, XNOR gate. So all the gates are realized by using NAND and NOR. Hence, these gates are called as universal gates. So similarly, in quantum computers, C0 gate is there, control NOT gate. Control NOT also called as universal C0 gate. We can realize all the logic gates, AND gate, OR gate, etc., NOT gate, XNOR, XOR, all the gates are realized by using C0 gate. Hence, C0 gate is called as universal quantum gate. Next, coming to other point, these gates are irreversible. What is this irreversible? Suppose if an output is given to you, then you have to predict what is the input value. What is the input value? Suppose if an AND gate is given, AND gate comes under, you all know, classical computer, correct? So if AND gate output is 0, then what is the input value? What are the input values? You cannot say it is a 0, 0. It may be 0, 1. It may be 1. Cannot say exactly one value, right? You are not in a position to predict the output, in a position to predict the input values. So then it is called as irreversible gates. Similarly, a reversible gate means depending upon the output, you can predict the input value. You can predict the input values. So in in quantum computers, all the gates like Polis X gate, Polis Y gate, Z gate, Hadamard gate, S and T gates, all are reversible gates. Depending upon the output, you can predict the input values. Hence, these are reversible gates. But when it comes to classical computer, the gates are irreversible. We cannot predict the input depending upon the output. Okay. Next, serial processing. Here, a serial processing, after completing one task, it will follow another task like this. But when it comes to quantum computer, like machine learning, it accepts huge amount of data. It accepts huge amount of data and do parallel processing operations and provides multiple solutions to a single problem. For single problem, it will produce multiple solutions. Depending upon the solution, it will predict or it will optimize which is the best solution to your problem. Right? So that is the main advantage of quantum computing. That is the one of the application of quantum computing, that is optimization. Right? Next. So what are the applications of classical computer? Like we are all using web computer for web browsing, gaming purpose, data storing purpose, watching movies, etc. Whereas quantum computer solves the complex problems which cannot be solved by the classical computer. Solves the complex problems which cannot be solved by the classical computer. Examples are factorization. Factorizing a large, it will take actually classical number of steps. But when it comes to quantum computing, it will use Shor's algorithm called Shor's algorithm. It will complete the factorization process in square root of n number of steps, exponentially faster than the classical computer by using Shor's algorithm. Comes to database search. It uses unsorted data to search a value from the unsorted data. Here we are using Grover's search algorithm. Grover's search algorithm. Similarly, it uses square root of n number of steps to search the particular value from the unsorted data. And then optimization. We already discussed about optimization. So this is the difference between classical computer and quantum computer. Yeah. Next, quantum with cloud. Are you clear with this? If you have any doubt, please ask me. Or shall I continue? Yeah. No doubts. Okay. Right. So quantum with cloud and backend. Suppose I am sitting here with a laptop, my laptop. So I want to write a quantum program, but I don't have a quantum processor in my laptop. So how can I do? Suppose I want to do factorization, a larger value, or I want to do optimization problem. I want to solve the optimization problem, and I want to do a database search. Database search. So for these applications, classical computers won't use. So we have to use quantum computers. So, but I'm not having the quantum processor in my laptop. So for that, first of all, what I need is in my laptop, first of all, I need to install Python. today we will discuss and do some hands-on like small projects. Python above 3.9 version. First of all, I need to install Python 3.9 version and above. And then I have to install a quantum programming language called as Qiskit. Quantum programming language called as Qiskit. Next, these are my requirements. And then I have to use the cloud because I'm not having the quantum processor in my laptop. So I have to use cloud. So different companies provides cloud servicing. So we all know Amazon provides AWS, service. Microsoft provides Azure. Azure. Third one, Google also provides Google Cloud, G Cloud service. And then importantly, IBM. IBM provides Qiskit runtime. This is important. Qiskit runtime. This is the cloud service name. And then backend device. I need backend device. I need backend device. What are the backend devices available? So IBM uses backend means execution device. IBM uses IBM Brisbane. Brisbane. This is the backend device for IBM. Next, Amazon uses what you call OCTEL. OCETEL. This is the quantum processor. This is also quantum processor prepared by IBM company. OCTEL is prepared by Amazon and Microsoft. It has its own quantum processor named as Mazorana. 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 Right. So similarly, Google also has its own quantum processor called as Sycamore. Sycamore. These are all the quantum processors. So first of all, I need to install to solve these problems, these type of problems. I need to install Python 3.9 and above version, and then I have to install quantum programming language, that is Qiskit, and I have to select the cloud platform, and then I have to select the backend device. So I have selected everything. So I installed Python 3.9 version. I installed Qiskit in it. So I have written my program. So in that, what is the next step? I have to select the cloud. So here I am selecting IBM cloud. So Qiskit, this is the IBM based cloud service. That is IBM Qiskit. Okay. So whatever the program I have written, I send it to the cloud, IBM cloud, that is Qiskit runtime. Then after it will forward it to IBM servers. IBM servers. From that, it is transferred to control electronics. The control electronics, what it will do, it will take the code from the server and converts it into microwave pulses, which is having the frequency 4 to 10 gigahertz range. And then those microwave pulses are dumped onto the quantum processor, and then it will give the results in the same way. We will reach to the it will reach to the cloud and then to my laptop. I can see the results of it. So this is the process. So first of all, install Python 3.9 version, Qiskit, and then select cloud computing, cloud service, and then it will forward it to IBM server, and then to control electronics, and then to quantum processor. What is this quantum processor? Since we are using IBM server, no, so this may be IBM Brisbane. This is the backend device. Yes, hardware device. That is backend device. So similarly, the diagram can be shortened like this also. So I have installed everything. So step one is I have to write about pass manager. So the program is transferred to which cloud service I have to mention in pass manager. And then also instruction set architecture, ISA is called instruction set architecture. So the program is forwarded to cloud by using pass manager and ISA, and then it will target it to the IBM backend device, that is IBM Brisbane. Again, after computation, it will again reverse back to cloud and then to our system. So this is the way. Right. We can use quantum processor also from sitting at home. Yeah. So this is the quantum setup, complete setup. So what is this coherence time? Coherence time means the time at which the qubits remains in superposition state. Coherence time means it is the time where the qubits remains in the superposition state. So to remains in superposition state, actually qubits are what you call easily corrupted. So whenever the qubits are interacted with the environment, so in the environment we contain it contains noise, disturbances, dust, etc. So whenever the qubits interact with the noise or environment, it will loses its superposition state. It will collapse into classical state. So that should not happen. So that is why we have to increase the coherence time. So that means we have to maintain the qubits in the superposition state only. So to maintain the superposition state, we need to have the cold temperature. The cold temperature. The temperature is about 0 Kelvin or 10 to 20 millikelvins. Absolute zero or 10 to 20 millikelvins temperature should be maintained. So what are the materials used here? So we are using aluminum or niobium. These are the materials used in the quantum processor for the construction, for the setup of quantum processor, aluminum or niobium. So actually aluminum or niobium at room temperature, that is 27 degrees centigrades, what it will do? Collisions occurs. Collisions takes place at room temperature. When the collisions are taken place, then the resistance values increases. That means noise increases. Whenever the noise is more, it loses the coherence time. That means superposition state. It will loses the superposition state. Similarly, suppose if you are maintaining aluminum and niobium at 0 degree, absolute zero, or 10 to 20 millikelvin, not at room temperature, 10 to 20 millikelvin cold temperature, then aluminum and niobium acts as superconductors. Superconductors. For superconductors, we are all know resistance is approximately equal to zero, very low. Hence, noise is also very low. Hence, it will give the capacity to the quantum processor to compute complex problems. So, when it will get the computational power, when it is in superposition state only. So, to maintain the superposition state, we have to maintain the cold temperature. Cold temperature, right? So, for that cold temperature, we need a cryogenic environment. That is a large refrigerator-like structure. This is all refrigerator-like structure. So like this. Yeah, here quantum processor is there. So in that, what you are using in that pipeline structure, what you are using, so we are using helium isotopes, helium-3, helium-4. These are all called isotopes. Why you are using isotopes? Isotopes are having same atomic number but with a different mass number. So helium-3 and helium-4 are called isotopes. These isotopes at absolute zero temperature, that means minus 273 degrees centigrades or 10 to 20 millikelvin, they act as superfluids. See here. So at 10 to 20 Kelvin temperature, aluminum or niobium acts as superconductors. At absolute zero, helium-3 and helium-4 acts as superfluids. So that means viscosity is very, very less, very, very less. So, and then He3 and He4, helium-3 and helium-4 absorbs the temperature in it. Whatever the temperature is there, that will be absorbed by helium-3 or helium-4. So these 3 points are very much important. So first of all, we need to increase the coherence time. To increase the coherence time, we need cold temperature. So what are the materials? Aluminum or niobium. What are the temperature? What is the temperature? Absolute zero or 10 to 20 millikelvin. At absolute zero, aluminum or niobium acts as superconducting materials. Superconducting materials have resistance low, noise less, and then it has the ability to solve the complex problem which cannot be solved by the classical computers. Which cannot be solved by the classical computers. Yes. So see next, reversible gates. We already discussed. If the inputs are predicted, depending upon the output, then we can say that these gates are reversible gates. We know all quantum gates are reversible gates. So let us see how we can predict the input values depending upon the output values. Let us consider an inverter. Suppose if the output is equal to 0, we can say that easily the input is equal to 1. Depending upon the output, we are predicting the input. Similarly, if the output is given as 1, we can predict the input as 0. That means this NOT gate is called as reversible gate. So NOT gate is called as reversible gate. So in quantum computing, NOT gate can be represented with the letter called X, or plus. So whatever the symbol you can choose, X or plus. If ket 0 is given, then we can get ket 1. Similarly, ket 1 is given, then you can get ket 0. So NOT gate or X or plus, whatever the symbol you can use. Similarly, XOR gate. So it is also called as reversible gate. See, first of all, XOR gate is a classical gate. No, so suppose if the output is given as 0, so you have to predict the input. So it may be 0 0 or it may be 1 1. You cannot predicting the output. Sorry, you cannot in a situation to predict the exact input depending upon the output. So that means it is not a reversible gate. You are not predicting the input depending upon the output. So it is not a reversible gate. But by doing some small changes in it, you can change the classical gate into quantum gate. So see here. So here A, B are the inputs. You are taking A to output. A can also be taken as output. See here, inputs A, B, outputs A XOR B. Now see, so 0, 0 here. Yeah. XOR gate can be written as like this. XOR gate can be written as like this. We know inverter can be represented like this. So if you use 2 lines and X, then it is called as XOR gate. So here the bit is called as control bit, and here the bit is called as target bit. Okay. So suppose whenever the control bit is equal to 1, then whatever the input is present at the target, that will be reversed. If 0 is there, then we can get 1. If 1 is there, then it will get 0. Suppose if the control bit is 0, then whatever the input is present at T, that will be forwarded to output. 0 is there, then you will get 1. Sorry, 0. If 1 is there, you will get as 1. Right? So see here. So first of all, 0, 0 is given. Since these two are inputs, A, B are inputs. What are the outputs? A is one of the output and A XOR B is another output. Correct? So see here in the table, A is one of the output and A XOR B is another output. So here also A XOR B is another output. Suppose if A is equal to 0, then it will deactivate the X gate. So what happens? This 0 is forwarded to output. So if input is 0 0, then the output is also 0. Similarly, 0 1 is given. So since 0 A is equal to 0, that will appear here. Since A is equal to 0, it will deactivate this X gate. That means the 1 will be forwarded to the output. So then 0, 1 is given. What is the output? 1. Next, 1, 0. Here see, 1 is given. So that means it will activate the X gate. So what happens when the X gate is activated? So it will invert the value present at T. So this is target bit now. So it will be inverted and forwarded to the output. Forwarded to the output. So 1, 0, 1 output. Similarly, last case. Here last case also 1 is there. That is why X gate is activated and 1 value present at B is inverted and transferred at the output, transferred to the output. So 1, 1, then output will be 0. See, this is the table for XOR gate. So 1, 1, 0, 1, 0, 1. Next, similarly, 0, 1, 1, 0, 0, 0. So we are predicting the input values depending upon the output values. So now now XOR gate also converted as reversible gates. Initially, XOR gate is not a reversible gate, but now after giving the extra connection like this, you are converting XOR gate to reversible gate. Similarly, you can do AND gate also. So AND gate, you all know AND gate is a irreversible gate. But if you are doing, so see here, this is control bit, this is control bit, this is target bit. So we can say that CCX gate, CCX gate. So XOR gate is called as, since control bit is 1 and X. So CX gate. So control not gate. Yes. AND gate is CCX gate, control not gate. So you can try on your own this one. Okay. If you want to see this in Algar set, that is like a software tool, we can what you call, you can draw the diagram on the Algar set. So see here, we are using Algar set. Okay. Yeah. So see, Alga, ALGA, SSERT, Algar set, algaset.com. So that's it. And then quick, just a drag and drop only. Yeah. So this is the window of Algar set. So first of all, what you are doing, X gate. So drag and drop here. Since you are applying ket 0 to X gate, what you will get? 1. So here you are getting 1. See here, you are getting 1, logic 1. You can see here also. Decimal value 1. Yes. So now you can change to, suppose if you click on ket 0, it will change to ket 1. Then immediately it will show ket 0. That means off state. Off state. So similarly, control gate, XOR gate. So this is the control bit. So drag and drop here. So first of all, control bit is equal to 0. We are checking, sorry, XOR output. Yeah, control bit is 0. Then what happens? The target bit is transferred to the output. So 0. Next, 0, 1. Target bit is transferred to the output. Next, 1, 0, 0. That means it will be inverted. Since if you click on this, it will change to ket 1. And then 1 is there. For AND gate, whenever the input, both inputs are 1, then the output will be 1. What happens? So whenever the input is equal to 0, the output will be 0. Input 0, 1, then the output will be 0. Similarly, 0, 0, output will be 0. So 0, 1, output will be 0. Next, 1, 1, the output will be 1. So in this way, you can create AND gate by using Algorithm tool. Okay. So the tool will be very much useful in doing quantum error corrections. Quantum error corrections. Okay. So yeah, similarly, you can do this also. OR gate. I will explain OR gate. By using OR gate, you can draw what you call full adder. So see here. How can we obtain the OR gate? OR gate means we know A plus B. A plus B. That can be obtained by writing A bar and B bar whole bar. By applying De Morgan laws, we can get A plus B. That is the output of OR gate. Correct. So we have to draw the diagram for this. For A bar, you are using an inverter gate. For B bar, you are using another inverter gate. And then AND gate is there. So see here, this is AND gate. I have drawn like this. But AND gate. And then since whole bar is there, I put an inverter at the output of the AND gate. So this is the logical diagram for OR gate. OR gate. So see here. So you all know how to draw an inverter. So you know inverter can be drawn like this. Simple X. Correct? So again, simple X. A bar. B bar. Correct? Right. Next, we have to draw an AND gate here. First phase is completed. You have to draw AND gate in the second phase. AND gate. How can you draw the AND gate? AND gate is also known as CCX gate, no? So control, NOT gate. Control, NOT gate. So this is called AND gate. Second part is over. So next, at the output of the AND gate, what we have to draw? An inverter. Inverter means again X gate. Inverter means X gate. So this is the output of OR gate. So see here. So this is the diagram. Right? So this is the diagram. You can draw it on Algar set also. So A input is given to X, then you can get A bar. B input is given to X, then you can get B bar. By drawing control, NOT gate, you can get AND gate. After that, if you draw a NOT gate, then you can get the output as OR gate. OR gate. Okay. So you can try on this your own by using Algar set. Next. So if you are having laptops with you at present, then you can try this it out. You can try this it out. So XOR gate, you all know how to draw XOR gate. So control X is called as XOR gate. And again XOR gate is there. One more control NOT gate. And then AND gate is there. Control NOT gate. Another AND gate is there. Control NOT gate. And OR gate is there. You know, now only you have drawn OR gate. So OR gate is there. So this is the diagram. So see here. So first of all, this is the XOR gate. And then control and X gate. That means from this you are getting AND gate. So with these two, you have completed half adder. Again, similar diagram. Control NOT and then control X gate, AND gate. So here you are getting another half adder. Now you have to add these two half adders. This half adder and this half adder. You have to add. For adding, we are using OR gate. OR gate. You know how to draw OR gate. So X gate, and then control, NOT gate. So here another X gate you need to put whenever you are using a 0 here. If you are using 1 here, then you need not to put another X here. No need to put another X here. See in the previous example also. So see here. If you are taking 1 here, then there is no need to take another X again. If you are taking it as 0, here. If you are taking here as 0, then you need to put an extra X gate. If you take 1 there, then no need to put an extra X gate. Okay. So optimization. With the minimum number of gates, we are constructing a full adder. So see, shall we try this? Please let me know. Shall we try this on Algar set? Sorry. Please respond. Shall I try this?
Yes, sir.
Yeah. We will try, or shall we forward? If you say yes, I will try it on the Algar set. No means I will forward to the further slides. Please respond. Okay. Then what are unitary operators? All are saying unitary operators, unitary operators. What are the unitary operators? Suppose if you take identity matrix, that is 1 0 0 1, we all know. What is the inverse of it? So that is also 1 0 0 1 only. If you multiply these two, if you multiply I into I inverse, if you get as identity matrix again, then it is called as unitary matrix, right? So 1 0 0 1. So multiply this, you can get 1 0 0 1, again I value. That is the reason why identity matrix is also called as unitary matrix. Similarly, Hadamard operation. Hadamard gate means 1 by root 2, 1 minus 1. This is called Hadamard gate operator. This is also unitary operator. So S gate is there. S gate means S is equal to 1 0 0 I. This is called X gate. So Polis X gate can be represented as 0 1 1 0. You have to remember all these gates. Y gate, Z gate. Suppose Z gate is there, 1 0 0 minus I. So similarly, number of gates are there. Okay. So there are basis states. 3 types of basis states. What are they? Single qubit basis state, 2 qubit, 3 qubit. So first of all, we start with single qubit. So single qubit means ket 0 and ket 1. So that can be represented as column vector 1 0 0 1. Suppose we are combining these two, we can get the identity matrix, 2 by 2 identity matrix 1 0 0 1. Similarly, 2 qubit basis state. So since 2 qubits, we can get 4 possible outcomes. So 0 0 0 1 1 0 1 1. So see here. So 0 0 can be represented as ket 0 0 can be represented as ket 0. This is called tensor product. Tensor product. So tensor product of 0. If you calculate this, you can get ket 0 0. Similarly, if you need ket 0 1, that is the tensor product between ket 0 and ket 1. Ket 1 and ket 0. Ket 1 and ket 1. So see first example, this one. So ket 0 tensor product ket 0. So ket 0 means we know 1 0. Again ket 0 means 1 0. So how we can calculate the tensor product? So see here 1 0 tensor product, again 1 0. So see, first multiply this with the entire matrix. So that means 1 into 1 0. Now take the second bit 0 and multiply with the entire matrix. This is called tensor product. So 1 into 1 1, 1 into 0 0, 0 into 1 0, 0 into 0 0. So this is called tensor product. Similarly, if you do this, you can get 0 1 0 0. If you do this, get 1 tensor get 0, then you can get 0 0 1 0. Similarly, if you do this, then you can get 0 0 0 1. If you combine all these, you can get 1 0 0 0, 0 1 0 0, 0 0 1 0, 0 0 0 1. So this is also identity matrix of 4 by 4, of 4 by 4. Correct. Similarly, 3 qubits. See here, identity matrix with 4 bits. Let us consider 3 qubits. So 0 0 0, 0 0 1, 0 1 0. So total 8 possible outcomes. So how you can get 0 0 0? By taking the tensor product between get 0, get 0 and get 0. So similarly, multiply this on your own. 1 0, 1 0, 1 0. So first I multiply these two. Then after I will multiply with this one. So 1 0, yeah. 1 into 1 0, 1 0, 0 into 1 0, 0 0. Finished. Next, tensor product between these two. 1 into 1, 1, 1 into 0, 1 into 0, 1 into 0. Again, 0 into 1, 0, 0 into 0, 0 into 0, 0 into 0. Done. For this one, you will get 0, 1, 0, 0, 0, 0, 0. Next one, 0, 0, 1, remaining all zeros. So similarly, you can get the matrix like this with 8 bits, right? So this is also column matrix. Next. So quantum gate with single qubit. This is important thing. Quantum gates with single qubit. So yeah, single qubit. So here I am taking Polis gates. We know Polis gates are of 3 types: X gate, Y gate, and Z gate. X, Y, Z. So X gate means 0, 1, 1, 0. 1, 0. So sigma X is the Polis X gate. So here I am considering get 0, get 1, and here bra 0, bra 1. Bra 0, bra 1. We have to take like that only. That is the syntax. So get 0, get 1, bra 0, bra 1 for all the things for single qubit quantum gates. Next, 0, 1, 1, 0, you have to put here 0, 1, 1, 0. This is called outer product calculation. Outer product calculation. So see here, whenever you find 0, you neglect this bra 0 and ket 0. Neglect that one. Whenever you find 1, then convert this ket 0 as, sorry, this bra 0 as ket 0 and convert this ket 1 as bra 1. Bra 1. Similarly, here also 1 is there. So convert this bra 1 as ket 1 and convert this ket 0 as bra 0. Bra 0. So then we can find like this. We can get like this. Ket 0 bra 1 plus bra 1 ket 0. This is the equation for Polis X gate. Polis X gate. So you are applying a ket 0 to X gate. So what you have to get ket 1, you need to get. Correct? So see, we are getting or not. So X ket 0. See here, I am doing ket 0. So that means ket 0 bra 1 plus ket 1 bra 0 into ket 0. Ket 0. Since the input is ket 0, no? So I am multiplying the equation with ket 0. So ket 0, no need to multiply. you have to multiply this ket with bra. So ket 0. So ket 0 into bra 1. So ket 0 into bra 1. That means here we will get 0 plus ket 1 bra 0 and ket 0. That means you will get 1 because both the values are same. So you will get 1. Whenever both the values are opposite, then you will get 0. So ket 0 into 0, 0. Ket 1 into 1, ket 1. So that is equal to ket 1. See here, you are getting ket 1 only. Here, ket 1 only. Whenever the input is ket 0, you will get ket 1. Similarly, do it for yourself. Ket 1 is given as input. So for this also I will do. Next one you have to do. Plus ket 1 bra 1, bra 0 into, this time I am multiplying with ket 1. Ket 1. So see, ket 0 bra 1 into bra 1. So ket 0 into 1. Same values, no? So 1 plus ket 1 into bra into ket, but with opposite values 0 and 1. That means you will get 0. So that is equal to ket 0 plus 0. That is equal to ket 0. So you will get here ket 0. Since input is equal to 1, output is equal to 0. Why? Because it is a NOT gate. NOT gate. X gate is also called as NOT gate. So in this way you can get. Similarly, calculate the outer product for Polish Y gate. Y gate means Y is equal to 0 minus I 0. So put it here, 0 minus I 0. So similarly, ket 0, ket 1, bra 0, bra 1, you have to take. See, since 0 is there, no need to consider. 0 is there, no need to consider. Now minus I is there, you need to consider. Minus I into, yeah, tell me, minus I into this bra 0 can be converted as ket 0. Ket 0. This ket 1 can be converted as bra 1. Bra 1 plus, next here I is there. This bra 1 is converted as ket 1. Again, this ket 0 is converted as bra 0. Bra 0. Right? Now you have to multiply, one second. So here and I into, sorry, I forgot to write I. Okay. Next, we have to take Y gate and applying 0, ket 0 as the input. So see here, Y is equal to minus, sorry, Y ket 0 is equal to minus I into ket 0 bra 1 plus I into ket 1 bra 0 into ket 0. So multiply this, minus I into ket 0 into ket 0. So no need to multiply ket 0. Both are opposite. Bra 1, ket 0. That means 0. Plus I into ket 1 into bra 0, ket 0. So you will get 1. So see here, this will become 0. So this will become I into ket 1. So I into ket 1. So see here, you are getting that one only. I into ket 1. These are very much important to solve the quantum circuits. So you have to know how to calculate the outer product form and inner product form. Okay. So first of all, we are calculating how to compute the outer product. Right. So similarly, you can use this equation for input ket 1. So you can get minus I ket 0, minus I ket 0, minus I ket 0. Okay. Right. So similarly for Z gate also, you have to do. So for Z gate, if you apply ket 0, you will get ket 0 only. For ket 1, you apply as input to the Z gate, then phase change occurs. Minus ket 1, you will get. Okay. Next thing, Hadamard gate. We already discussed Hadamard gate. 1 by root 2, 1 by root 2, 1 by root 2, minus 1 by root 2. So this is called Hadamard gate. So here, here we have to consider all the values. 1 by root 2 into ket 0 bra 0 plus 1 by root 2 into ket 0 bra 1 plus 1 by root 2 into bra 0 sorry bra 1 ket bra sorry ket 1 bra 0 minus 1 by root 2 into ket 1 bra 1. In this way you have to write the equation. Then after whatever the input you have to give, that you can give. So here I am applying ket 0. So multiply this with entire equation with ket 0. Ket 0. So you will get the final equation as 1 by root 2. This is most important. 1 by root 2 ket 0 plus ket 1. This is also called as h ket plus. H ket plus. Yeah. For S gate also, phase operations. P theta is equal to 100 e power I theta. If theta is equal to pi by 2, then you can get S gate. S gate. So, you know, e power I theta means what? Cos theta plus I sin theta. I sin theta. So, pi by 2, cos pi by 2 plus I sin pi by 2. So, you will get finally this one 0. So, I into this one value as 1. So, 0 plus I. So 1 0 0 I. Similarly, if you take pi by 4, theta is equal to pi by 4, then you get t value, t gate. That is 1 0 0 1 plus I by root 2. 1 plus I by root 2. You can use Qiskit. I will show it to you. You can use Qiskit. How you are getting these values without calculating. Now we are calculating manually. By using Qiskit, you need not to calculate manually. Just a simple command called operator. If you use the command operator, it will do for you. So it will give the S value, it will give the T value, it will give the Hadamard value, it will give the X value, Y value, Z value, all the values it will give. The simple command is operator. Okay, so we'll see next. Yeah. So these are all the things all the staff members or faculty before me covered. So 3 qubits. 3 qubits are of two types: Toffoli gate and Fredkin gate. These are all simple things. Then, yeah, important thing. So a simple series quantum circuit. Yeah. So single bit you are applying Y gate and then X gate. So you have to simplify this one. So how you can simplify? You have to start from right to left. So that means Yx is given here, but you have to consider xy. So you know x. What is the value of x? 0 1 1 0. You know the value of y 0 minus I 0. So both the values you know. Yes. So you know the equation of x also. This is came from outer product. This is the outer product of x value, right? So x ket 0, you will get ket 1. Similarly, you have to write the outer product for y value and then y ket 0. So you will get I ket 1. So you have to multiply these two, x ket 0 into y ket 0. So if you multiply these two, then you can get as I into ket 1. So this is the equation for what? Column vector 0 1 can be written as ket 1. 1 0 is there, then you can write it as ket 0. Since 0 1 is there, you have written ket 1. Okay, next thing. Similarly, this time ket 1 is given. I will share the PPT so you can try on your own. So everything is there in the PPT. Okay, next, similar thing. So parallel, this is what important. Parallel. So see, example 1. Hadamard gate is given and a straight line is given here. A straight line is given here. So whenever you find a bare straight line, you have to consider an I gate, identity gate is present here. Identity gate is present here. Okay, so see here. So H, since these two lines are in parallel, H tensor I. Whenever two lines are in parallel, suppose X gate is there, Y gate is there, Y gate is there. Then if you need to calculate this, then you have to use the tensor product. That is X tensor Y. Why? Because these two are in parallel. Similarly, H gate and I gate are in parallel. So you have to consider H tensor I. At the time, ket0 and ket1 are also in parallel. So you have to write ket0 tensor product ket1. So we already discussed it. Whenever you find ket0 tensor ket1, then you can simply write ket01. Ket01. So now simplify this one. What is this? H tensor I. So you know 1 by root 2 taken as common 1, 1, 1 minus 1 tensor product identity matrix 1, 0, 0, 1 into 0, 1. Get 0, 1. So 1 by root 2, put it here, and then 1 into the entire matrix tensor product. So 1, 0, 0, 1. Again 1 into entire matrix 1, 0, 0, 1. Again 1 into entire matrix 1, 0, 0, 1. Now this time minus 1 into entire matrix minus 1, 0, 0, minus 1. Careful, right? This one. And then don't forget this one. Ket 0, 1. Ket 0, 1 can be represented as 0, 1, 0, 0. We already discussed. Right? 0, 0 means all zeros. 0, 0, 0. Ket 0, 1 means 0, 1, 0, 0. Yeah. Similarly, since here you have 0, 1, that is the reason why 0, 1, 0, 0. Okay. Multiply matrix multiplication. Simple matrix multiplication. Then you can get 0, 1, 0, 1. So 1 by root 2 I have written like this, like that only. So 0, 1 means ket 0, 1. 0, 1. So this is the position of ket 0, 0. This is the position of 0, 1. This is the position of 1, 0. This is the position of 1, 1. So whenever the value 1 is present, take that value. So here 1 is there. So that is the reason why 0, 1. Here 1 is there. So take that value 1, 1, 1, 1. So this is the final output. This is the final output. So see here, you have to do this in Algar set. Parallel quantum circuit. So see, so clear all, or you can delete, or you can drag and drop again. So first of all, you need to take H gate. Here H gate is there. So just click on it and drag and drop here, H gate. And then a simple narrow line. So that is the reason why I am not putting any gate there. So that means it internally takes it as identity matrix. Identity matrix. What are the inputs they have given? 0, ket 1 are the inputs. So similarly, sorry, ket 1 is there. Ket 1 is there. So see here. So what is the output here? What is the output here? 1 by root 2, 0, 1 plus 1, 1. Correct? So whenever you will get 50%, then you can write it as 1 by root 2. Or you will see value is equal to 0.707. That means 1 by root 2. So see here, 1, 0 at the top, amplitude of 1, 0. And then see here, amplitude of 1, 1. 1, 1. So 1, 0 plus 1, 1. Here also you are getting the same value, no? So 0, 1, sorry. You have to take in the reverse order. Sorry. My bad. So 1, 0, no, amplitude of 1, 0. You have to take in the reverse order. So 0, 1, and then 1, 1, 1, 1. So you are getting the same value. So see another circuit. This time H and you have to solve this. This is most important circuit. You have to manually solve, and then you have to solve by Qiskit, and then you have to solve by using Algar set. These circuits are important because these circuits are called entanglement circuits or Bell states. Bell states. So I will explain the entanglement state with an experiment that will be more understandable in the easy way. Yeah. So Bell state. Let us consider H Hadamard gate. And what is this X gate? Control X gate. That means XOR gate. So here, suppose if the line is not given here, then it is simply a NOT gate. If a line is provided here, then you can say that it is an XOR gate. Control NOT gate is also called as XOR gate. So how to solve this circuit? We have to start from right to left. So that is the reason why I have written first C naught, and then Hadamard gate. Since a narrow line is there, you have to think an identity matrix is present here. So H tensor I. Why tensor comes here? Because these two are in parallel. So H tensor I, and then 0 tensor 0. Yeah, 0 tensor 0. We can write ket 0 0. So see here, C naught, no change. Hadamard gate, H tensor I. We already done this H tensor I. Yeah, here. So this is the value H tensor I. So same value I'm getting here H tensor I. This time what? 0 0. So 0 0 means 1, remaining all zeros, 0 0 0. Right? So now you have to multiply this with entire matrix. So see here, I'm giving a small what you call a trick. You need not to multiply these two matrices. So you can follow the trick. So the trick is whenever you find C naught on the left side, then you need to change the third and fourth rows. That's it. You need to change the third and fourth rows are interchanged. See, this is the zeroth, sorry, row now. So 0th row, first row, second row, third row, or first, second, third, and fourth. If you take from 1, this is second, third, fourth. You need to change what? Third and fourth rows. So third row becomes fourth row, and fourth row becomes third row. So see here, compare these two. So 0 1 0 minus 1, 0 1 0 minus 1. So 1 0 minus 1 0. So 1 0 minus 1 0. So you need not to multiply with again C naught, right? So then after you multiply with this value. This is the simple multiplication now. So need not to multiply with C naught gate, because C naught means it is also a 4 by 4 matrix. 4 by 4 matrix. So 1 0 0 1 0 0 0 0 0 0 again 1 0 0 1. Next 0 1 1 0. This is the CX matrix, control not matrix. So see, 4 by 4 matrix, again multiply with 4 by 4 matrix. You will get again 4 by 4 matrix. So you need not to multiply that one. So you simply follow the trick. Whenever you find the C naught gate on the left side, you just interchange the third and fourth rows of it. That's it. So you will get the same result. Otherwise, you can try it on your own. So now multiply this value, this matrix with this one. So after multiplication, you will get this. So see this value, get 0 0 0 1 1 0 1 1. So say what is the value of it? 1 by root 2 get 0 0 plus, since these two are not taken, since here 1 is there, and get 1 1. So this is called Bell state or entanglement state. Sir, why or how you are calling it as entanglement state or Bell state? So we will discuss it further in further slides. So see here, this is a Bell state or entanglement state. Since we cannot split those things. Yeah. So see here, now C naught is on the left side of the diagram. So start from the right side. So first you have to write H tensor I, then after C naught, then after tensor 0, ket 0, tensor ket 0. So similarly, H tensor I, you will get this one, C naught into ket 0 into ket 0 tensor product ket 0, you will get this one. interchanged. Third and fourth rows are interchanged. Whenever you find third and fourth columns are interchanged, it will save your lot of time. Suppose if you are multiplying that one, you may get the chance, you may get the errors. But if you follow the trick, it will give the correct answer. So since C naught is on the right side, C naught is on the right side, you have to interchange third and fourth, because I have done many examples. So all are perfectly correct. So that is the reason why I am explaining here. C naught, if you get the C naught on the right side, you have to interchange the third and fourth columns. So first column, second column, third column, fourth column. So third and fourth are interchanged. So 1 0 minus 1 0 becomes 0 1 0 minus 1. 0 1 0 minus 1 becomes 1 0 minus 1 0. See here. Yeah. Now multiply this one. You will get this one. So 0 0 0 1 1 0 1 1. So see, since 1 is there, you have to consider this one. Anyhow, 1 by root 2 is present here, 1 by root 2. So again, 1 is there, you have to consider this one, 1 0. So this is not a Bell state. My bad. So this is not a Bell state. Not a Bell state. Because you can take the 0 as common. So we can split here. We can split here. That is the reason why it is not a Bell state. It is not an entanglement state. In entanglement state, we cannot split the states. We cannot split the an example. So suppose entangle means two or more particles are state of the one particle defines the state of the other particle. That is the definition. The definition may be lengthy, but it is more meaningful. Two or more particles are interchanged. Sorry, two or more particles are interlinked in such a way that the state of the one particle determines the state of the other. So I will give you a simple example. Suppose if you are having a pair of shoes, so left shoe and then right shoe, right shoe. So this is kept in a box. Left shoe is kept in a box and right shoe is kept in a box. You interchange those things many times. Many times you have interchanged this one, right? So suppose one shoe is sent to America. Another shoe is sent to Russia. Lots of distance is there between Russia and America or India, whatever. Okay. Suppose in America, you have opened the shoe and you have find the right shoe is there. So to find the left shoe, you need to go to Russia. You need to go to Russia. No need to go Russia. You can estimate, you can expect the left shoe is present at Russia. So why? Because these two are shoes, pair of shoes interlinked. So if you find the state of one shoe, that is right side shoe, then you can expect or you can predict the other shoe, left shoe, is present at Russia. Or if you are finding left shoe at America, then you can predict that you know need not to go to Russia. You can predict the right shoe is present at Russia. Okay. So this is the entanglement state. So these two are interconnected, no matter how far the distance between them are. So still they are interconnected. Okay. So that is called entanglement state or Bell state. And one more experiment is there, no? So I will tell you that one also. Yeah. Suppose
Excuse me, sir.
two electrons are present.
Sir,
Two
Ashraf, sir.
electrons are present. Okay.
Sir,
So,
Ashraf, sir.
ma'am.
So kindly conclude with this experiment, sir, and
Okay,
the
sure,
tomorrow
ma'am.
session we can continue.
Sure, ma'am. Sure, ma'am.
Yes, please.
Sure. Yeah, thank you. So let us consider two electrons. Two electrons. These are completely isolated. Suppose say it is in one room, it is in another room. There is a wall between these two electrons, right? Suppose it is spinning in positive z direction and it is also spinning in positive z direction. Let us consider a stringer-like structure, which is forming a magnetic field in the positive z direction only, and a wall is there here. A wall is there. Okay. Here also a stringer-like structure, magnetic field in the direction positive x direction. Again, wall is there. Wall is there. Okay. Suppose this electron is passed through this magnetic field, then there is 100% probability that it will fall on the top. 100% probability. Since this is also in the positive z direction, whenever it transmitted through the structure magnetic field, it is also having the probability of 100% that it will fall on the top. Then we can consider this as, since on the left side it is having positive z direction, then you can take it as ket 0 for left side. For right side electron also positive z direction, you can take it as ket 0. So in the tensor product you will get ket 0, ket 0. Sorry, ket 0 0. Similarly, if left side electron is in the negative x direction, a wall is there, and the electron is in the positive x direction. Again, stringer-like structure, magnetic field, it is in positive z direction. See here, a wall is there. Again, it is transmitted through, again, stringer-like structure, magnetic field in positive z direction, and a wall is there. So it may be fall on the top, it may be fall on the bottom. That means a 50% probability to fall on the top, a 50% probability to fall on the bottom. Similarly, here also we cannot predict. It may be fall on the top 50%, it may be fall on the bottom remaining 50%. So we can consider like this. Since it is in negative x direction, we can consider as ket minus. Since it is in positive x direction, we can consider it as ket plus. So consider tensor product. You have to simplify that one. Okay. Last slide. Last thing. Suppose if you consider a particle, it is having zero momentum. Angular momentum is zero. So after some experiments, it decaying as two electrons. One is in the, suppose it is in clockwise direction, another one should be in anti-clockwise direction, because total angular momentum becomes zero, because the original particle has angular momentum zero. Because of some experiments, we can split it as two particles. One particle should be in rotating in clockwise direction, another particle should rotate in anti-clockwise direction. Now again, let us consider the stringer like structure. After passing through this, a wall is there. Again, stringer like structure. After passing through this, a wall is there. So these two are also separated. See here, if it is fall on the top, definitely, see here, it will fall on the bottom. 100% probability. We can predict. Because why? Because these two are spinning in opposite directions. So we can predict. Suppose if it is fall on the downside, 100 with 100% probability, then it will be, it not maybe, it will be fall on the top side with 100% probability. So how it will happen? Because the total angular momentum is equal to zero. So that is the reason why if it falls on the top, a right side electron falls on the top, left side electron should fall on the bottom. If America finds the shoe as a right shoe, then Russia will find the shoe. Definitely it will be left shoe only. Or America is finding the shoe as left side, then Russia will find automatically it will be on the right side shoe. Yeah. So why? Because these two are a pair of shoes. A pair of shoes. Because here these two are came from one particle. One particle. So that is the reason why if you find the state of this particle on the top side, then you find the state of this particle on the bottom side. On the bottom side. Similarly, if you find the state of the particle on the bottom side, then you definitely find the state of this particle on the top side. On the top side. So this is the experiment of entanglement state. So I hope it will be clear to you. Ma'am, shall I stop here?
Yes, sir.
Yeah. So is anyone having any doubts? Please let me know.
Participants, if you have any queries, you can raise the queries now.
Thank you.
You can raise your queries in the chat box also.
If possible, so tomorrow I will continue on Quiz Kit for half the period, and remaining half the period, if time permits and madam give the permission, then I will go for VLSA. Yeah. Yeah, please ask. Sure.
I think no more queries, sir.
Okay. Link. Ma'am, someone is asking link.
They are asking for feedback links, sir. I'll provide to them.
Okay, okay.
Mm.
That is what important.
Yes, sir. Thank you so much,
Okay.
Dr. Rashtrapati, sir, for your valuable time and valuable insights. Your patience is highly
Sure.
appreciated. And
Thank you, ma'am. Thank you.
I'll give the brief summary that you have given so far. Sir has
Sure,
detailedly
ma'am.
explained about the difference between the classical computers and quantum computers, and Sir has clearly highlighted how classical bits operate in fixed binary states while quantum computers harness the power of superposition and entanglement to perform
Yeah.
exponentially complex computations. Sir has given a brief description on quantum computing with cloud and backend platforms, helping us understand how today's quantum processors are accessed remotely and how jobs are executed through quantum cloud services and how the backend architecture manages qubit operations. Following that, Sir also elaborated on the essential requirements for quantum computers, including cryogenic temperatures, isolation from environmental disturbances, and the decision and the high precision requirement needed for maintaining quantum coherence.
Yes.
Um, he also gave the insights about the specialized materials used in quantum processors, such as superconducting circuits, trapped ions, and semiconductor qubits, which enable stable and scalable quantum systems. Further, he also explained a clear understanding of quantum error correction techniques, emphasizing their importance in preserving qubit stability and computational accuracy. And Sir has given insights on various quantum operations using polygates and how these fundamental gate operations from the building blocks of quantum algorithms. He also explained entanglement states with practical examples illustrating how two qubits can share correlated states even when physically separated, and how this unique property is utilized in quantum communication and computation. Sir also illustrated qubits and quantum gates with practical examples, making the operational behavior and the logic of quantum gate functions clear and easy to grasp. Hope everyone enjoyed the session. Lot of practical information is there in this session. And tomorrow we have two more sessions. Tomorrow we have 3 sessions. Just a minute. Tomorrow the session will start from 2 o'clock onwards, 2 to 3:30 p.m. The session by Dr. B. Leela Kumari Garu, and she is an associate professor and HOD Department of ECE, JNTU, Kakinada. And the topic is AI-driven signal processing techniques. And next 2 sessions from 3:30 to 5 and 5 to 6:30, hands-on training session by Dr. Ashraf Ali sir. He'll continue the same session tomorrow, and if time permits, he'll discuss about VLSI and quantum computing. Sir, is it right?
Ma'am, we'll inform you.
Okay.
Sure.
Okay, sir.
Sure. Thank you, ma'am. Thank you.
Thank you. Thank you so much, sir, for your valuable time. And the participants have already shared thrice this feedback and attendance link in the chat box. I'll share it again. Please check it once in the chat box. And tomorrow the session will start from 2 p.m. onwards. I'll share the detailed link as well as, link details as well as the session details tomorrow as a reminder to you in the WhatsApp group.
Emma, tell me about exam link also.
Okay, we will provide the exam link tomorrow in the last session. That is in between 5 to 6:30. After 6:30, around 6:30, you will receive the link through WhatsApp and then in the chat box also. And for the registered participants, we will share through mail also. Someone is facing unable to join in the WhatsApp group, so we will share through mail also. And after the exam, after feedback session, there is a valedictory section from 7:30 to 8 p.m. Ma'am, did I miss anything? If you want to tell anything, please.
Nothing, ma. It is clear.
Okay. Kindly submit the attendance and feedback link as early as possible. Thank you so much, guys. Thank you for your patience listening. Take care and have a nice day ahead.
Good night, ma'am. Thank you.
Good night, sir. Thank you.